We will be talking today about image classification, basically continuing our discussion on the topic of image classification from last lecture. And we'll get a little bit into some topics that gets us closer to neural networks and ultimately convolutional neural networks and so on. We'll start with linear classifiers. Moving to the next slide. This was the syllabus that we've talked about last lecture, in the previous lecture, where we did talk about three major categories of topics: deep learning basics, perceiving and understanding the visual world, reconstructing and interacting with the visual world as the three major topics, and some sub topics that we will be covering in the class. And at the end, we will have some discussions around the human-centered AI aspects. And today, the goal is to cover the first three items: data-driven approaches. I will try to tell you what this means, and linear classification, as well as the k-nearest neighbor algorithm. So, like the previous lecture, let's start with our core task of image classification. Again, it's a core task in computer vision, and we actually come back to this task quite often throughout the quarter because it's a very good benchmark, and we have some examples to tell you how the algorithms work. So this is one of the items that we come back to quite often. We want to define the image classification task today, and then introduce two of the data-driven approaches for image classification. One of them nearest neighbor, and the other one a linear classifier. There are some other approaches which we have listed in our backup slides, and you're welcome to look at them after the class. But this is what we will be covering. So what is image classification? Given an image and a number of predetermined labels, a set of possible labels, such as in this example you see dog, cat, truck, plane, and so on. The job of the system is to assign one of those labels to this image. So to us, this is actually a very, very easy task because our brains, our cognitive system, is wired to get a holistic understanding of this image and assign a label to it. But when it comes to coding this and looking at how a computer can make sense of this image, that's completely a different story. And we want to see how machines can make sense of such data. So images are often defined by matrices of data, more broadly, more generally, tensors of data. And often the numbers are, each of the pixel values are between 0 and 255, which is an 8-bit data structure. And since this is an image, a colored image, assuming that it's with a resolution of 800 by 600, since it's an RGB image, it has 3 channels of red, green, and blue RGB, and therefore it's a tensor of 800 by 600 by 3, as you can see on the slide. So, as you can probably guess, this is the semantic gap between our perception of this image and how the machine perceives and sees the image, right? And in order to be able to even understand how this could be very challenging. Let's look at some challenges, some variations in this type of imaging data. So let's assume, for example, as one example, let's assume that we move the camera. If the camera is moved, for example, panning the camera around, even if the cat sits completely and perfectly still, all of those pixel values, every single pixel value of 800 by 600 by 3 will be changed. So all these pixels will have a new value. Again, for us humans, it's the same object. There's absolutely no difference. But from a computer's perspective, it's completely a new data point. So this is one of the challenges, but there are quite a few others as well. For example, illumination is another challenge. So if you've seen or if you've taken courses in graphics or maybe other vision courses or digital image processing courses for engineering applications, you know that the value of each RGB pixel, the RGB values, are a function of the surface material, color, and their light source. And that's why same cat, same object may look differently in terms of numbers when it comes to being pictured in different illumination conditions. With that in mind, so whether the cat is in a dark room or under the sun, still it's the cat. It's one cat, but this is creating challenges for the machine. Can you maybe name some other challenges that may change the values of the pixels and create problems for the machine to recognize objects, other than illumination and viewpoint changes that I mentioned? So background clutter, background objects, yes. Which is actually our next slide. Yes, background clutter is another challenge. Anything else? Zooming in and out, yes. So a scale basically of the object in the image. Yes. What else? The resolution of the image that could be considered as that's definitely a challenge. But often with machine learning models or any model that we want to recognize objects in images, since we normalize the size of the image, resolution may not be that important unless there is zooming effects of the objects. Occlusion is one of the major problems. Again, as humans, it's very easy to say, this is cat, these are cats. Even the last one, which is actually a very challenging, the one on the right, you can only see a tail and a little bit of probably paw in the right side. One could say, yes, that could be a tiger, or it could be, I don't know, a raccoon with a tiny tail. But because of the context, because we know this is inside a living room on a couch, most probably it's a cat. It's a cat. So again, for us humans, it's not that hard. Beyond that, there are many other problems. Deformation. Cats are very deformable. So they create challenges for algorithms to be detected, recognized. I mean, not today's algorithms, generally for building step-by-step algorithms that can detect objects. So deformation is one of the other major challenges. And beyond that, the intra-class variation is one more important challenge. We know that cats can come in different sizes, colors, patterns, or even they have different breeds, and all of those are still cats. But for the machines, it's not that easy to recognize the intra-class variations. One other interesting challenge is the context, because if you only look at that part, that image on the right, or if an algorithm looks at this without considering the context, it's very easy to classify this as a tiger or some other animal. But because of the context, and because we know there's the effect of shadows and so on, this could probably be classified correctly. So, but the thing is that the classifiers that we have today can do really great good jobs at classifying the images, identifying the objects in images, thanks to efforts like ImageNet and also all of the follow-up works that created larger scale benchmarks for training larger scale models. And in this class, what we want to do is to get to a place that we build models that can recognize objects and also other aspects within the image. For the rest of this class, we are going to be working towards building step by step the building blocks that are needed for building those large algorithms. And before doing so, we have to look at the most basic building block of classifying an image, and that is implementing a function like this. So if you've taken some of the computer science or engineering courses that often build frameworks through algorithms, like for example, sorting as a computer algorithm, it often comes with some if-then-else rules and some for loops and so on. So there is a clear flowchart of tasks and steps, if-then-else steps that creates an algorithm for sorting. But when it comes to images and understanding the visual world, that is not happening. That is a challenge. There is no way to hard code the steps for classifying images. Although there has been some efforts in this space, there are papers that they've tried to come up with algorithms and steps to recognize objects. And one of those was based on edge detectors, finding the edges in the image as a first step, and then after creating all of these patterns, look at the important patterns, for example, corners, extract some features that are around the corners, or counts the number of specific types of corners, and based on those, from those, try to map that into the output class. So while this is been an interesting effort and it had some success on very limited variability of type of images, but this is very hard to, first it's very hard to scale these types of algorithms. Even if it works, it's very hard to scale because you have to create these rules and everything for every single object that you want to recognize. And second, finding the logic for each of those requires a lot of effort by itself as well. So because of these challenges, I think these types of algorithms, which are based on creating logics and procedures for detecting objects or classifying images, have not been quite successful. And machine learning comes with this data-driven approach. So with this new paradigm and another paradigm of looking at this problem from a data-driven perspective, we define a procedure of a three-step process. And the first one is to collect data sets of images and their labels. So there are many different ways of, so if you want to recognize a specific type of object, or specific types of objects, we can look for data sets or single data points over the internet to create a data, many samples from each of the examples. We used to be doing this 10, 20 years ago using search engines and image search engines over the internet to create these types of data sets. Now we have all of the data sets. So, and then the second step is using machine learning algorithms to train a classifier. Basically, build a function, train, that takes the images in the training data and their associated labels and builds a model that can associate images with the labels. And then the last step would be evaluating the classifier on new images, which means implementing a function called predict that takes the model and some test images, and for those test images that were not part of the training images, predicts the labels and returns those as the output. So a very simple procedure, but instead of building a logic, we are building a data-driven approach for it. As I said, we want to talk about two popular methods and classifiers. One of them is nearest neighbor classifier. This is the easiest form of classification. And we specifically want to go over this because we can learn some of the concepts around building these classifiers, and it's easier to explain some of the details, and then we'll move to the topic of linear classification. Okay, to do that, what we do to build the nearest neighbor classifier, as I said, we need to build the train and predict functions. The train function needs to just memorize all of the data and labels. So the training function basically doesn't do anything other than keeping everything in the memory. And then the prediction function, the predict function, looks for the most similar training image. Basically, it creates a lookup table of all of the images and all of their labels. And during the prediction or testing time, what it does is tries to find the closest one, the most similar image, and output the label for that image. Let's look at an example. So assuming that we have these 5 as in our training data, then, yes, you see my cursor. And then this is the query image, the input image for prediction. What we want to do is to see which of these training data and training images is the most similar to this one. And for that, we need a distance function. So this distance function needs to take the 2 images, each pair of images, each of these images compared to the query image, and return a value which defines the similarity between these 2 inputs, these 2 images. There are many different ways of doing that. One of the most popular ones is L1 distance, which is defined as the sum over all absolute values of pixel differences between the 2 images, image I1 and I2. As an example, if this is a testing image, if we want to calculate the distance of this image with an image in the training data, we do a pixel-wise subtraction and the difference between the pixel values, and then sum them up, which defines this value as the distance between these 2 images. So this is the most basic distance function, but it's actually very useful in many applications. We'll be coming back to this L1 and other variations of distances in the class quite often. With this very simple definition, we want to see how we can get this implemented. As I said, the first step is to just memorize the training data. So the train function just keeps the data in the memory, and then what the predict function does, using actually some Python libraries and NumPy and so on, we can implement this in just 4 lines. We calculate the distances between each of the testing samples and the training data, take the minimum for each of the testing samples, and then output the label for the one with mean index. So this is going to be the implementation for the predict function. Yeah, the pixel values, as I explained, the simplest form. This is a tensor of 800 by 600 by 3, and 3 channels, and these are RGB values for each of the pixel locations. So yes, I should actually repeat the questions for online students too. And the question was the pixel values, what do they represent? Yeah, so the next question is why it's between 0 and 255. So there are many different standards for storing images. The most popular one that we use in almost all images that you see online and here, they are RGB. RGB is a 24-bit format, sometimes 32 because there's another channel alpha. We don't want to get into those, but the 24-bit format, it means that for each of the channels, for each of the 3 channels of red, green, and blue, which create all color combinations, we can have 8 bits. So that's the standard that is defined. There are some other frameworks too, but this is the most popular one. So with that, let me go back to the code and ask you a question. So I know some of the students, most of the students come with engineering backgrounds and a little bit of computer science as well. But we want to see with, say, N examples that we have in the training data, how fast the training and prediction happens. I'm hoping that you're familiar with the big O notation that we often represent computational and sometimes space complexities with. But here, if you look at the algorithms, I'll go with the training data. In the training function, and then I want you to help me with the answer for prediction. For the training step, the training is of O1 because we are not actually doing anything. We are not even moving any data. We're just keeping the copy of the data in the memory. So no operations. It means that without operations, with operations of order 1, we can complete the training step. What about the prediction step? For each of the single examples of the testing data, how many operations should we take? N. Yes, if we have N training data, it means that we have to calculate the distance of every single testing image with all of the images in the training data. So at least in the order of N operations. So this is not really good, because what we often want to do is, because training is not doing anything, but during testing, during prediction time, we are spending so much time just to do comparisons between the data and each single data point and the training examples. this would be similar to the fact that each single time that you ask ChatGPT a question, it will try to see what the answer is and compare it with all of the possible answers over the internet, which will take years, and then return your response, right? So it wouldn't work when it wants to scale. For very simple problems, we used to be using these types of approaches. So what we often want is to build classifiers that are fast during prediction. They do it much faster, but it's okay if they take a lot of time to do during the training, because that could be done offline. So with that in mind, although there has been a lot of efforts making nearest neighbor much faster using GPUs and so on, which are beyond the scope of this class. If you're interested, you can take a look at those. But with that, I want to look at some of the visualizations and how this algorithm in general works. So given this space that we have 5 classes of red, blue, green, purple, and yellow, and each dot represents one training sample in that class. If we partition the space for every single point, you see that we can create these 5 partitions, let's say 5, or in this case 6 different partitions, that each point, if we have a testing sample that is in that specific region, the color of that region shows what the nearest neighbor for that sample will be. So this is going to be the nearest neighbor algorithm, one nearest neighbor algorithm, partition the space in this setting. But do you see a problem here in this example? So the yellow one is in the middle of all of the greens, and this means that probably that's an outlier. That's probably a noise, and this is the case for many, many problems that we have to solve. And with that, the reason that there is this big yellow region in the middle is just this single point, and because we are only using one nearest neighbor, this happens. So to make it a little bit more robust, we can increase the number of nearest neighbors that we take, which turns the nearest neighbor algorithm into a k-nearest neighbor. And we often select more than one point or sample, and we often take the majority voting for identifying the label for any given testing sample, testing image. But the problem that you can see here is now we have some white regions. Those white regions are areas that we cannot make a decision, a complete decision, because those areas are areas that we have equal number of samples from the neighbors, from the 3 different classes. And there's no way to identify what the label of that example in the white region is. And for you, if you create these types of spaces for your problems, this means that if you look at these spaces, it means that those are good regions to go and collect more data for. So those are unclear spaces. So it's a good way of finding regions that are important for data, more data collection. Okay, so we can go larger on the value of the k, but one of the choices that we have, one of the factors that plays an important role is the value of k. But if you remember, we had another decision to make, which was the distance function. We talked about the L1 distance, again, sum of all of the absolute values between pairwise differences of the pixels. And if I visualize the L1 distance, or sometimes in some contexts we call it Manhattan distance, the distance function is kind of visualized in this way. If I calculate, if I look at this square that I have in this space, all of the points on that square they have a same distance from the origin, from the center point. So this is a good way of visualizing and seeing how this L1 distance function works. Another popular framework, another popular distance function that we use is L2, which instead of the absolute value, calculates the square of the differences, sums it up, but because of the square, we also do a square root. And visualizing that, we'll get this circle visualization where each of the points on the circle they have the same distance from the center, from the origin. So this visualization actually helps us understand the differences between these distances too, and these are the most basic and easiest distance functions that we can use. So there are, again, a lot more. The reason this visualization is helpful is because sometimes if you rotate so X and Y in these two visualizations are basically the features. If we have 2 pixel values, two features, then we have this 2D space, and this X and Y are often those features. So if I rotate these features, meaning if I use other types of features, this L1 will have a different framework, different value, while it's not any different for L2. So that's why this is a big difference between L1 and L2. And sometimes if our features are very specific and meaningful and we want to preserve their information, often L1 is more important, is better, because it has kind of, as you can see, a shape that preserves and enforces distances based on the features. But if features are more arbitrary, then L2 distance makes more sense. If I want to calculate the distance, so the distance of all of the points on this shape from the origin are exactly the same, right? If I use the L1 distance. But for L2 distance, the points on this circle have the same distance from the center or the origin of this space. So that's basically the main, what these two images are showing. Any point on this shape, when using an L1 distance, have the same distance from the origin. And for the circle, any point on the circle, if we are using L2 distance, will have the same distance from the origin. Yeah, why it's important is better to use L1 if we want to preserve the features. So to answer that question, if I rotate the feature axis, the distances and this distance function changes completely, right? While if I do the same here, nothing changes. It's the exact same value of the features, right? Distance, sorry. So in this case, L1 is very sensitive on the feature values, while L2 is not. If you select another feature in the same space that is having a different, creates a different shape, then your L function, the distance function changes as well. So if I draw the lines here, again, the question for online students is why it changes if we rotate. If I select another feature that goes from this side, right, then the lines will look different, right? So if you rotate this thing, but for that shape, it's agnostic, right? So with these two distance functions that we talked about, if I revisualize the space, you can see with k equals to 1 with one nearest neighbor, with L1 and L2, these are the space partitionings. One of the interesting things that you can see here is that with L1 function, most of the boundaries are parallel to the two axes, the two features. X1 and X2, very much sensitive to the features, while there we have a little bit of more smooth boundary separation. So there is a tool online on the lab website that you can play around with this, with different distance functions and different number of k. You can create a different setup, so you can play around with it. But why did we talk about nearest neighbor to begin with? First, yes, it's the easiest problem to solve, easiest solution, easiest data-driven approach, and great to start with. But one of the main reasons that we want to iterate and discuss nearest neighbor is the fact that we can look into the topic of hyperparameters. Hyperparameters are often some of the variables that you have to make a decision on to be able to run your algorithm. In this case, the value k, the number of nearest neighbors, is defined is a hyperparameter. Depending on how many number of nearest neighbors you take, your outputs will be different. And then another choice that we have here is the distance function. So the choice of hyperparameters are often very much dataset dependent and sometimes problem dependent. And we have to have a way to identify those, to kind of optimize for them for each single problem. And that's what is often referred to as hyperparameter tuning in machine learning algorithms, in deep learning algorithms, and so on. And how to do that, how to set the hyperparameters, there are different approaches. One of them is to choose the hyperparameters that work the best for the training data. So you have a set of images or data in your training data. You look for the best set of hyperparameters that generates the best training or minimum training loss. While it works for the training data, it's not a good idea at all, because especially with nearest neighbor, k equal to 1 is always the best value, right? Because you're memorizing training data, so k equal to 1 will give you always the 100% accuracy. So we know that this is not a great idea. The second one is choosing hyperparameter that works best for a held out testing set. While this is a little bit better than the first one, there is also a big problem here. Can anybody say why this is a problem? Exactly, so it's kind of cheating, because you are trying to find the best hyperparameter that works on the testing data, and you don't know how the model will work on any other data points, not in the testing set. So yes, that is exactly right. It's not a good idea because we don't know how the model will generalize, and for sure never do this. As we talked about, it's kind of cheating. And a better idea is to always take some part of the training data as validation set and train your model on the training data, on the train portion of the new portion that we call train, and then try to find or optimize your hyperparameter on the validation set. And after you've found the best set of hyperparameters, then use those hyperparameters to replicate the results for the testing set and do the predictions for the testing set. So this is a much better approach, although it does have some challenges itself, because sometimes the validation set that you've selected, it may not be a good representative of the entire landscape, because your validation set is almost always much smaller. And that's why one of a better approach is to use cross-validation for setting hyperparameters. Basically, you split your training data into a number of folds, a number of partitions, here in this case 5, and each of the folds plays as the validation set once, and iteratively you run this 5 times for 5-fold cross validation. You do this 5 times and average the accuracies. So you set a value of the hyperparameter, you run this for all these 5 sets, define the accuracy, calculate the accuracy on the validation set, average it. And then you do this multiple times to find the best setting for the hyperparameter. After you found the hyperparameter setting, you apply it to the testing set. This is a little bit more reliable and generates much better results. Although in larger scale deep learning, it is less practiced because repeating this multiple times and 5 times with huge data sets is very hard. So we often use intuitions for setting hyperparameters, and the single validation set is sometimes the approach we go with. But this is pretty much advised, again, outside computer vision, outside larger scale data sets. Often research papers require doing these types of cross-validation and these types of statistical frameworks to make sure your results are reproducible on a testing set. Anyways, so there are different approaches. Let's finalize the topic, wrap up the topic of nearest neighbor, and look at some examples, some results. So let me introduce you to the CFAR10 dataset. It's one of the datasets that you're going to be using in your assignments quite often. It has 10 classes with a number of training images and testing images. The 10 classes, some of the examples are shown here. With nearest neighbor, for each of the testing images, if we run nearest neighbor and select the top 10 nearest neighbors, they are all visualized there. As you can imagine and guess, one of the first questions to answer is how many, what should be the value for K? How many nearest neighbors should we take? And one study, one of the quick experiments with 5-fold, each of those points is one of the folds in 5-fold for each of the values of K, shows different values here, and as you can probably see here, K equal to 7, it generates the best results in terms of accuracy, which is close to 28% accuracy, which is actually not too bad because this is a 10-class classification problem. And with a 10-class classification problem, often the random guess gets you a 10% accuracy. So this is much better than random guess. So it's working, it's doing something, but there's a lot of room to improve. So if we go back and look at the examples, we can actually see there are so many mistakes, especially with the one that is closest. For example, the 4th row, if you look at that, it's a frog, but the first example seems to be a dog. And you can guess why this is happening, because the distance is being applied on pixels. And pixel-wise, they look like each other. They have the same type of colors in most pixels, so they are much closer. This example and many other examples show that distances that work on pixels and pixel values are not the best choices. We never practice them. There are much better approaches that we'll be discussing at the end of more in the future lectures. And just to wrap up the topic, this is another example. If you look at this original image, those 3 images, while they look very much different in terms of color or maybe occlusion, or the one in the third one from the left side is just same pixel. It's the same image with 1 pixel shifting to the right, I think. Although from a human eye's perspective, there is absolutely no difference, but the distance between that and the original image is the same as the other two examples that you see here. I'll stop for a couple of questions, and this is the summary of what we discussed. So the question is how we make a decision, right? That's in those cases, we often go with randomly select one of the tops. So if you are to collect more data, if you're, for example, you're solving a problem now in genetics, or you're solving a problem in medical imaging, when you visualize your examples, your features, or whatever, and then in this nearest neighbor space, you do see pockets of a space that you don't have any good samples for, or there is ambiguity, then you often try to go and find other samples that lie in that same area, in that space. Okay, so summarizing what we've talked about with K nearest neighbor, it was mostly about understanding the easiest algorithm, data-driven approach, and then talking a little bit about hyperparameter tuning and how distance metrics and the value of K play a very important role. Moving on to the next topic, which is linear classifiers, 25 minutes time to cover this. I want to spend the remaining time of this lecture to talk about this very important topic. This is the most important building block for almost all of deep learning, and we need to see how this approach is different. So first, we want to see how it's different from nearest neighbor. So this is a parametric approach, meaning that now we are learning, we are finding some parameters, W, or some weights that map the input image into the output classes, the output numbers. In this case, when we create this function f that maps input to the output, often those outputs are kind of membership scores of the image to each of those 10 output classes labels. So with this setup that we build, a linear classifier first maps, uses W, uses these parameters to map each of the inputs X into a value, which is the output Y. And how this is done is very simple. This image is basically an array of, say, 32 by 32 by 3. So 3072 numbers. And this defines our X, which is 3072 by 1 vector. And we know that we have 10 output classes. So we need 10 different scores. And the scores are, the output will be kind of a vector of 10 by 1. And this means that we have to identify, to find a weight matrix, W, that is a 10 by 3072, that maps X into the output scores. Just to complete this linear function, we often use this bias term as well. It's an input independent value, which actually has a lot of different use cases. I can talk about it when I do some geometric visualizations, but it sometimes creates a shift for different class scores, and helps with much better separation of each class. So as I said, these linear functions are actually building blocks for building neural networks. Each of these linear classifiers, linear functions, when put together one after the other, create these large neural networks. Although there are a lot of other things that need to be added here, but this is one of the most important components. If we look at some of the popular neural networks, we can see that linear functions are everywhere in the architectures. So to better understand what this mapping and this function is doing, let's go back to our example of CFAR10 and our training and testing samples and so on, and even make it a little bit simpler. Instead of looking at large images of 32 by 32, let's look at images of 2 by 2, an input image that has 4 pixels. This means that the input image is turned into a vector. As you can see here, we have to find a W and the values of B. So the input image is mapped into some scores as the output. So this is how the linear function from an algebraic viewpoint looks like. The output scores, here we are considering 3 classes of cat, dog, and chip. And as you can see, this function maps the image, the vector representing the image, into those scores. So algebraic viewpoint of linear classification. Now let's look at some visual perspectives of this linear classifier. As you can see, we often create these, each of these images as we talked about for this image. For each of the classes, we define some sort of, we have a row of this row in the matrix W, right? So this row is kind of a template for that specific class. If I separate it like this, so this image is multiplied by W and B, and W is, this is the template from each of the 3 classes of cat, dog, and sheep. And after training or building the model on the CFAR data set, if I look at the visual perspective, a visual viewpoint of the linear classifier, if I look at those templates that are learned for each of the 10 classes, you can see these templates. So it's very interesting that in some of these cases, for example, for the example for car, you do see a front of a car template-ish. And although this is all done with just one linear classifier. So the visual aspect, visual viewpoint of the linear classifier. And there is another aspect of geometric viewpoint. What this linear classifier often does is finding those lines, if it's in 2D space, finding those lines that separates each class from the others. And as you can see here, red, blue, and green are defining different classes. And in higher dimensional space, instead of those lines, it's these hyperplanes, as you can see in this example on the left. So you can also see the use of the bias term here, because if we didn't have the bias, all of these lines should have passed through the origin from the center of that space, which doesn't really make sense. But with the bias, we can actually create more reliable functions and decision boundaries. So a linear function is very useful. A linear classifier is very useful for many applications, as we talked about, and it's a building block of more complex neural networks, but it does have its own challenges because it can't classify many instances of separate data. For example, in this case, if class 1 is the first and third quadrant and the second class is second and the fourth, there is no way to linearly separate these. Another example is if we have this type of separation between class 1 and class 2 that shows the distance from the origin being between 1 and 2 as class 1 and then everything else as class 2. Similarly, if there are 3 modes, 3 areas in the space that are one class and then the second class is everything else. So in all of these cases, it's actually very hard to do the separation. So what we should do, so we talked about the linear classifiers and how they can actually map the input images into any form of labels in the output. But now what remains is how to choose the value W that for each of these images maps the image into a score for each single class as the output. And in order to do that, we need to define a loss function, sometimes referred to as objective function, that quantifies how bad the classifier, how bad the model is working. So the level of unhappiness with respect to the score on the training data. After defining those, we need to find a way to efficiently change the values of W to be able to minimize that unhappiness, basically minimize the loss function. And this is the optimization process, so the topic of next class, next lecture. And in order to do that, again, for simplicity, let's look at a easier example, having these three classes, a linear function, as you can see here, and the three classes of cat, car, and frog. We need a loss function that tells how good our current classifier is, and in order to do that, we need to parameterize the problem, xi and yi defining the input images and the corresponding labels, and then we need a loss function, a distance function that maps, looks at the differences and how bad the scores are compared to the ones that are predicted, the predicted scores, f, x, and w, and the ground truth values, the values that are already given, y, i's. We often normalize them based on the number of samples as well, but it's not that important. So this defines the loss function, the objective function. So how we can do the optimization and how can we really find the W's? There are different ways of defining this Li, and I want to talk about Softmax classifier right now. As an example, for that cat, if you remember, the scores that were given were 3.2, 5.1, and a minus 1.7. These are the scores that are the output of the function we discussed, f, x, I, and w. And in order to turn these scores, because these scores are unbounded and the values are often not very much controllable, because this is just a linear function, right? In order to turn these into some scoring functions, the best possible way is to turn these into probabilities, which defines the probability of the class being this class K for each input image Xi, right? And in order to do that, we first, this is the function that we use, the Softmax function. We first exponentiate the values of the scores to create these numbers. When we use EXP on these numbers, the numbers will always be, the outputs will always be positive, right? And we need to make sure that the probabilities are always positive. And after creating these numbers, what we can do is just normalize them. So exponentiate and then normalize based on the sum of all of the samples, right? So then we normalize them based on sum of all samples, and this creates very good set of values that define a probability function. So this is a distribution function, they sum to 1, and if I want to interpret these, it's very simple to say it's this set of W's, parameters, thinks that this image is a cat with a probability of 13% or 0.13, right? And obviously, this is making a mistake in this example because the W is not a good setting. We should optimize it and change it. So these probabilities are the counterparts of these unnormalized log probabilities, which are often referred to as logits. So if you've taken other machine learning courses, or if I'm sure in other fields you've used logistic regression, this is a similar type of framework. This is the exact same framework as logistic regression. And since we have multiple classes here, it's a multinomial logistic regression. How do we define the function L? I told you that there are different ways of defining the function L. We want to define a loss function that, what's the objective here? We want to maximize the probability of the sample belonging to the correct class, right? So we want to maximize the value of 0.13. Now we have other larger values in that set. So if you want to maximize this is a maximization problem, right? In order to turn it, because all of the objectives that we define, we try to build a minimization objective function. The first step is just to negate the values, right? We negate it, so the maximization problem turns into a minimization problem, and then we also take the log of the value just to make the numbers a little bit more manageable. So negative log of that value will define the objective function, the loss function, for solving this problem. Very simple. That's the objective or the loss function for Softmax. And for this logistic regression function. And if you've taken, as I said, other classes like CS231N, it's often referred to as maximum likelihood estimation as well. It's the same algorithm. So with that in mind, I want to say that, so as we discussed, it's the negative of the log of that probability of the correct class, which defines the objective function, the loss function. And that's basically that simple. But there are other types of interpreting this framework as well. So one way of redefining this loss function is saying that we have some estimated probabilities, and we also have a probability function that defines the correct probabilities. What we want to do is to match these two probability functions, right? And in order to do that, we want to minimize the KL divergence, callback error divergence. This is a information theoretic perspective of looking at this loss function. And again, those are exactly the same. This KL divergence in this setting simplifies into the same negative log function that we defined. And even going further, this is exactly the cross entropy function, because if we define this, use this entropy of P, which is entropy of the correct values, correct probabilities, plus that same KL divergence, again, this simplifies into the same negative log function, and that's because when we use one hot encoding setting for the classes, the entropy is 0. So that's one of the reasons that we call this function cross entropy or binary cross entropy function. In all of deep learning, you've probably, if you've used any of the neural network frameworks, you've heard about BCE, binary cross entropy, or you will be hearing about it a lot. So this is the same framework, we start very simple, but we got to the similarities and differences between each of those. So the objective, the loss function was defined as negative log of this probability, and the probability was defined by the softmax, which we talked about, and then optimizing for this, which is the topic of next session, will give us the right W's. But before I end, I want to ask a couple of questions with this definition that you see here. What is the mean and maximum value that you can see for the loss function Li? Yes, it's 0, which turns into minus infinity, but we have a negative negation there, so it will be infinity. That is correct. But then we also have to, yes, that's definitely, that's right. And let me actually look at a second question. Yes, this one. So when we initialize all of the SIs, so basically the W's, in the beginning it's almost random, so the probabilities of each of the classes becomes mostly equal. What is the softmax Li, assuming we have C classes? And especially if it's C10. So because the probabilities are equal, it means that all of the probabilities are around 1 over C, right? And then that will be defined as log of C, and we have 10. If we have 10 classes, then the log or ln of 10 is 2.3, which is the EXP we know about it.